In this session, we will discuss about the stress-strain diagram. We all know that there are a lot of metallic materials available nowadays in market. We have developed certain materials also. So before we use any material or before we select any material for a particular application, we need the mechanical characterizations, or in simple words, we need the mechanical properties. So in order to obtain the mechanical properties of engineering materials, we adopt different characterization methods. So one of the characterization method is tensile test, and using the tensile test we obtain a stress-strain diagram. Now let us go ahead and see how the test is being conducted and how the stress-strain diagram is plotted and what are the inference that we can make using the stress-strain diagram. Stress-strain diagram are obtained using a tensile test. Tensile test is conducted on a machine called as UTM, Universal Testing Machine. The image that is given here is the computerized UTM. So UTM consists of an upper jaw and a lower jaw, between which we are going to place the specimens. So the norms which is given over here controls the hydraulic fluids which is flowing into the system, the motorized system, and thereby it regulates the movement of upper jaw as well as the lower jaw. And what the computer does here is it gathers the information or the deformation happening on the specimen which is kept in between these two chucks, and after interpreting the data it plots a stress strain curve. There are analog type of or manual type of tensile machines available, in which the entire reading or the load values will be obtained in a dial. So we have to manually take down the values and we have to do the calculation by our own. That is the way the system works. If it is a computerized one, it will collect all the data values and it will process it, and we will get the output as a stress strain diagram and all the necessary values associated with it. Now let us discuss about the specimen, because specimens are very much needed, or the study of the specimens are very much needed so as to understand the mechanical properties and to compare the mechanical properties. So the images that is given here are some of the different tensile specimen that we use. It is generally comes under two category. One is a flat type, another one is a round type. The size will vary based upon the standards. These specimens are fabricated based on some international standards. So these standards are provided to us by American Society for Testing and Materials, ASTM. It is called as ASTM. So ASTM is an international agency that gives us different standards so that we should follow while fabricating these materials, and the instructions or the condition that we should maintain or how the test should be conducted. All these things are being specified by ASTM standards. So we have to follow these standards, then only we will be able to compare the results that we have obtained in an international platform. Now let us discuss in detail about the nomenclature of the specimens. So the total length of the specimen is called as overall length. On the either side it has got grip section. This portion is going into the chuck, so proper gripping should be there. So you can see the round specimen, there are threaded portion on the grip section. This is mainly to ensure that there is a proper contact or there is no slip happens between the chuck and the specimen. And one important portion is the gauge length. So because the importance is that we expect a failure to happen between the gauge length. The entire reading is measured in between this gauge length. So the marking of gauge length is very much important, because the computer needs some input data to do the calculations. So one of the input data is the gauge length Another one is the diameter or the area, cross-sectional area. So these are some of the input values that we give to the computer for the calculation purpose. So we are not bothered about what is happening away from this this gauge length. So what we expect is to have a failure in between or in the gauge length. So the gauge length is a very important nomenclature, and before the test we have to closely observe the specimen and we have to mark the gauge length. Now moving forward, let us see how the testing is being conducted. These tensile specimens are placed between these chucks, and by adjusting these knobs we are going to strain the material. We are going to move this chuck in the upward direction. Thereby this chuck is going to create a tensile pull on the specimen. One chuck will be fixed, the other one will move. Thereby it will create a tensile effect on the specimen. So you just assume that we have a rectangle or a specimen over here. So it is going to start elongate once the load is applied. So this elongation is measured by using an extensometer and or by using a strain gauge, and these data are being fed to the computer. So those are the input data. For manual type of UTMs, there will be a dial from which we are going to measure the load, and we are going to correspondingly measure the deflection using the extensometer. So this deflection is we are measuring is in between the gauge length. So using these data points, a graph is being plotted, and that graph is called as the stress strain curve. So we all know that after some time the material is going to fail, it is going to break, and that breakage may happen in between the gauge length. So now let us go and see how a stress strain curve will look like. Engineering materials are generally categorized into two. One is ductile material and second one is a brittle material. Ductile materials are the one which has a property to elongate, or the ductility is very high. So the materials which can be drawn into thin wires are generally comes under the ductile material category. If you take the example as aluminium, steel, mild steel, or even one of the most famous metal among all of us is the gold. That is one of the most ductile materials that is available. So these materials can be drawn into very thin wires. That means the ductility is high. Such kind of materials will be categorized under the ductile material. And brittle materials are the one which will not undergo high deformations. So the failure will be all of a sudden. So we cannot expect to have a deformation, larger elongation, not deformation, larger elongation. Now let us discuss the stress strain curve of a ductile material. So before we move into the details of the stress strain curve, the y-axis is the stress and the x-axis is the strain. So the elongation from the gauge length or the data from the extensometer is used to obtain the change in length happened in the gauge length, and once we know the change in length we can easily calculate the strain because we have already noted down the gauge length value. So using the fundamental equation, change in length upon original length will give you the value of strain, and by using the constitutive relation, which is nothing but the Hooke's law, you can easily calculate the stress value. So I hope you all remember in the first class I have told you that the strain is a physical phenomenon or a geometrical phenomenon, and it can be measured experimentally. You cannot measure the stress. So the same thing is happening here. We are not measuring the stress, we are measuring the strain. So after measuring the strain, we using the constitutive relations, we calculate the stress. So that is a very important thing that all of you should keep in your mind. Now let us see what are the salient features of the stress strain curve. So when we start to load the material, slowly the stress strain is going to develop, thereby the stress, and gradually the stress and strain increases and it reaches a particular point. This point is called as the proportionality limit. So proportionality limit is the limit under which the stress is proportional to the strain. So the rate of change of stress and rate of change of strain will be same. So a straight line behavior is going to be obtained up to proportionality limit. And when we move further forward, we have another point which is going to come over here. So it is going to come very close to this proportionality limit somewhere here. We have one more point, and that is also a very important point, and that point is called as the elastic point. It is called as the elastic limit. So you have to understand the basic difference between elastic limit and proportionality limit. It is stated that within proportionality limit stress is proportional to strain, but even beyond the proportionality limit, even though the stress is not proportional to strain, when we release the load at this particular point, that means if we release the load at the elastic limit, what will happen? The material is going to retrace this curve and is going to regain its original shape. So that has to be understood very clearly. If we release the load at elastic limit, it is going to regain its shape. There will not be any kind of permanent deformation which is left within the material. So these 2 points are usually lies very close, so they are generally read together. But in ideal cases, we have to specify it as 2 different points as proportionality limit and elastic limit. And beyond this point, the material is going to permanently deform, and this particular point is called as the yield point. It is going to start to yield, and it has got an upper yield point and lower yield point. So this is a idealized curve, and after this, what will happen is the material is going to, again it is going to, even after the permanent deformation, the material is going to carry more amount of load. We can see the material has elongated and it is going to carry more amount of load, and this is the point which is called as the ultimate strength. That means this is the load, maximum load that this particular specimen will take, beyond which it will not take. So after this particular point, the graph is going to come down. So at this point, what is going to happen to the material? The material will start to neck. Necking will take place. Necking in the sense, the cross section is going to vary drastically, change drastically, and this necking is a physical phenomenon. It can be easily seen. You can see with your naked eyes. If you look at the tensile specimen, this change in or the necking phenomenon can easily be seen in the material, and it is an indication of a failure. It is the material is going to fail. We can infer that soon or later the material is going to fail. And further, when you increase the load, it cannot take much load, so the graph is going to come down, and at this particular point, what will happen? This necking will increase, and at a particular point, failure is going to happen. This is how we have to read the stress strain curve of a ductile material. So these are some important points: ultimate point, yield point, elastic limit, proportionality limit, all those things. And necking is going to start from this particular point. There are some other detailed points, or there are some other important points that we have to note down from the stress strain curve that we will discuss in the coming slides. So what is the difference between the stress strain curve of a ductile material to that of a brittle material? When you look at the graph, you can see the number of salient points are very much less in a brittle material because it is not undergoing some permanent deformation. Deformations are very small, so it will not show any kind of yielding. So at a particular point, it is going to fail. All of a sudden, it is going to fail. So if you look at the images of the specimen after the tensile test, you can see how the breakage has happened. Here you can see easily seen a cup and cone type of formation. So I told you that after the necking, it is going to fail, and after the failure, the material will be of this particular cup and cone formation will be there. So easily you can see a cup like structure is here and a cone like structure is here, but this kind of change in cross section or kind of cup and cone formation is not visible in the brittle materials. A cut and through kind of failure has happened in the brittle materials. So simply by looking at the failed specimen, we can easily say what kind of failure has happened in the material. And this is how you have to read the stress strain curve of ductile and as well as the brittle material. Now let us go and see what are the other salient points. You might have seen one dotted line is passing over this darker line, and we have to discuss the in detail about these two lines. Actually, the darker line which is drawn here is called as the engineering stress strain diagram. Engineering stress strain diagram. The reason why it is called as, see, in this type of engineering stress strain diagram, the initial data that is taken into the system, or for the calculation purpose we have taken the cross sectional area, and we are not considering the instantaneous change in cross section. We all know that at this particular point it is going to start necking, and thereby the cross section area is going to change. But that instantaneous change in cross section area we are not taking. We are taking the area as a constant value and we are plotting this graph, and that particular graph is called as the engineering stress or engineering stress graph. But if we consider the instantaneous change in area, then the graph is going to be something like the dotted line. So the graph will follow this dotted line and it will end up here, because as the area decreases, the stress value is going to increase. So this is a true stress strain curve and this is an engineering stress strain curve. So in all the application we will be using the engineering stress strain curve. So here also you can see this is the one line that goes, the upper side is called as the true stress strain curve, and this is called as the engineering stress strain curve. So a lot of features are available there in this stress strain curve. We have already discussed about the yield stress and the ultimate stresses. So another thing that you have to note down is the stress at fracture. What is the value of stress that the material has taken at the time of fracture? That is also an important value when we design something. So if you look at the various portions within this particular stress strain curve, the initial zone, that means the portion up to the elastic zone region, elastic point, is called as the elastic region, and the point which is going to come after the elastic point, that means after the elastic region, this much portion, this is nothing but plastic zone. So it is given here, plastic behavior, or the zone that is going to come after the elastic point is called as plastic zone, because the entire deformation is in the plastic region, it cannot be regained. That's why it is called as the plastic zone. And in our engineering studies, that means in the mechanics of solids, our entire discussion will be within the elastic limit. We are not discussing anything beyond the elastic limit, because the linear behavior is not available there in the plastic zone. Linear behavior is only available up to the elastic limit, so we will limit our discussion to this elastic limit. And if you want to study something in the plastic zone, we have to go for the higher mathematic operators and the differential equations we have to go for, because conventional type of equation, linear system of equations, cannot be used over here. So that is happening. Now within the plastic zone there are different areas. One is the yielding zone, where the initial yielding takes place. So another zone is strain hardening. So this is a wonderful phenomenon in which, so you know that when we apply a load, the energy that the material is going to absorb is increasing point by point. So after the yielding, after this particular point, what will happen is it will take enormous amount of load to have a unit deformation. So the amount of load that has consumed here for a unit deformation will not go at this point, or beyond this point we need more amount of load to have to produce considerable amount of deformation. It is simply because of the accumulation of deformations within the material, and that phenomenon is called as the strain hardening. So up to the ultimate point, up to this point, from the yield point, you will be observing the phenomenon called as the strain hardening, and after the ultimate stress, the another phenomenon of necking is going to takes place. This is how this curve should be read as. And another important stress that we have to note down is the proof stress. Proof stress. See, proof stress is nothing but the stress, or it is very difficult to distinguish this yield point, because this is a conventional type or ideal type of stress strain curve. In the real stress strain curve, you may not be able to see this dip or anything like that. It will be something like an arc, something like this. So this much kind of details may not be available. So the proof stress is nothing but it's an assumption that generally the yield point is available or usually obtained in material at 0.1 or 0.2 percentage of strains. So that is an important assumption that we make. That means in the case of proof stress, we assume, or we have an assumption, that 0.1 to 0.2 percentage of strain, we will consider this much amount of strain, and what we will do is we will mark the 0.2 percentage of strain somewhere over here. Let it be somewhere like this, at this particular point. And what we will do is we will draw a straight line from here. We will draw a line parallel from here, and we will extend it over here, and the meeting point is considered as the yield point. So the meeting point here, this is considered as the yield point. This is how we actually find out the yield point in a actual stress strain curve. So this particular yield point is generally called as proof stress, or otherwise it is also called as 0.2 percentage of yield stress. It is also stated like that. And one more type of stress is mentioned here, which is nothing but the working stress. What we do is, all the engineering application, or when we design something, we expect that our material should work within the elastic limit. So those stresses that is going to develop within a material within the elastic zone, those stresses are called as the working stresses. So if you take the equation for the percentage elongation, we can say that the final length minus the initial length divided by initial length is going to into 100 will give you the percentage of elongation. And if you take the percentage reduction in the area, the equation is going to be the initial area minus final area divided by initial area into 100. This much percentage of elongation and reduction can be found out using the stress strain curve. And now as I have told you that as we increase the application of load point by point, the material is going to absorb the energy. So that is the basic thing that is happening within a material. So at the elastic limit, when you release the load, the energy which is accumulated within the material is released. There, after releasing it, it will reach to the initial point. And at the plastic zone, it cannot release the energy, it will be accumulated. So we have to talk all these behavior under the energy absorbed. This energy absorbed is simply nothing but the strain energy. This is called as the strain energy. So strain energy is nothing but the area under the stress strain curve. That is nothing but the energy absorbed by the material. That is how you have to read the material. So the energy absorbed by the stress strain energy absorbed by the material is nothing but the area under the stress strain curve. Using this stress strain curve, we can discuss the different mechanical properties of the engineering materials. So you might have noticed here, compared to the previous graph, you cannot see any kind of yielding here in this graph. This is how the actual stress strain curve will look like, something like this. Now you cannot have directly, you cannot have a yield point here. So it is very difficult to obtain the yield stress here, and for that reason we are going to use the proof stress value to find out the yield stress. Now these are some of the major properties that we can discuss using the stress strain curve. Some of the major properties. One first property is the elasticity. That is very evident, or it's very easy to understand. Elasticity is the ability of a material to come back to its initial position when the load is released. That's how elasticity is being defined. And plasticity is nothing but the ability of a material to undergo permanent deformation. So don't think that plasticity is something a negative phenomenon. No, there are cases where plasticity, highly plastic materials are needed for forming applications or something like that. We need materials which have good plasticity. And ductility we have already discussed. And malleability is the ability of a material to deform, or to be ability of a material to deform into thin sheets. Such kind of materials are called as malleable materials. All materials are not malleable. We cannot say that all ductile materials are malleable. No, that kind of conclusion is not suited. Some materials are specially suited for making into sheets. Now comes the important property called as strength. How will you define a strength? Strength is nothing but the ability of a material to carry load. So higher the load carrying capacity means it is having a higher strength. That is how we will define the strength value. Strength value is nothing but the ability of a material to carry more amount of load. So we can say that if the material is high strength material, definitely this stress strain curve is going to have a steep inclination. It will not be a flat one, it will be a steep inclination. It will carry more amount of load without undergoing much deformation. That's how we have to understand the strength based upon the stress strain curve. And toughness is nothing but it is the amount of energy absorbed under the stress strain curve. We have already told that this energy is called as the strain energy. So the same strain energy is nothing but the toughness. It is highly tough. That means the ability of a material to absorb energy, that is called as toughness. Also, this energy is split into two. One is the total energy absorbed, and another one is the energy absorbed within the elastic limit. Suppose if you consider this as the elastic limit, and if you draw a line here, and if you take the area under this particular portion, so the energy absorbed within or till the elastic limit is called as the modulus of resilience. So that is also another important parameter which I have not mentioned here. So kindly make a note of that. So the energy absorbed within the elastic limit is called as modulus of resilience, and the total energy absorbed is called as the toughness. And another property is hardness. This is also a very important property. Hardness is the ability of a material to resist surface deformation or surface penetration. If a material is hard, means it is very difficult to deform or penetrate the surface. And that is how the hardness is being defined. And now comes the stiffness or rigidity. Stiffness is nothing but the ability of a material to resist deformation. So if there are some materials where in which we have to apply more amount of load to deform it, so such kind of materials are called as stifferments, or that particular property is called as stiffness. So, or else in other mathematical formulation we can say that stiffness is nothing but force per deflection. Force upon deflection is defined as stiffness. So these are some of the major engineering properties which can be read from the stress strain curve. Also, if the material is not having that much amount of stress, then the curve is going to be a bit more flat. And if it is highly ductile, means this area is going to increase the length of the graph, the x-axis is going to increase. So all these things can be easily associated with the stress strain curve of an engineering material. So using this stress strain curve, it is easy for us to define the Hooke's law. Hooke's law is defined within the elastic limit. It's a very, very important, or the first law that you are going to learn here is the Hooke's law. So Hooke's law is something which is defined within the elastic limit. That has to be taken into account, elastic limit. So what Hooke states is that within the elastic limit, the stress is proportional to strain within the elastic limit. So you please don't get confused. actually we have discussed that the stress is proportional to strain only up to proportionality limit. So this is only valid up to proportionality limit, but the elastic limit lies very close to the proportionality limit, and even when you release the load at the elastic limit, there will not be any kind of strain left within the material. So that is why it is being defined as within the elastic limit. So within the elastic limit, stress is proportional to strain and the behavior is linear. So it makes the calculation very easy. So to change the proportionality sign, a constant is going to come in the picture. That constant is called as E. E is nothing but modulus of elasticity, or otherwise it is called as Young's modulus, which is named after Thomas Young, who proposed this constant. So usually this Young's modulus value is another important parameter. So this E is obtained simply by obtaining the graph of the stress strain curve in the elastic zone. If you plot a graph like this, if you take the slope of this, the value is nothing but E. That is very simple mathematics. So Young's modulus is calculated within the elastic limit. So usually the value of elastic limit, the Young's modulus is for steel is between 200 to 210 gigapascals. The Young's modulus value is generally given in gigapascal range. That is easy for standard practice of giving the value in gigapascals. So when we compare all the equations that we have learned till now, we have learned the stress equation as load upon area, we have learned the strain equation as change in length upon original length. So if we compare all these equations, what we can say is, if you substitute stress as load upon area, and if you substitute strain as change in length upon original length, and if you rearrange, you can easily calculate the equation for the change in length happened on a material. So P is the applied load, L was the initial length, A was the initial cross-sectional area, and E is the Young's modulus of a material. So unit homogeneity has to be maintained. If you substitute everything in meter, all terms should have a meter term, or if you use mm, then everything should be in mm and load should be in Newton. So then only you will get the value of dl in corresponding units. So how can you define this equation? It is very simple. The total deformation happened on a material of length L and cross-sectional area A with Young's modulus E when it is acted upon by a force P. Or in other words, we can say it like this: when we apply a load P on a material with cross-sectional area A and length L, whose metallic Young's modulus is E, then the total deformation happening on that particular material is nothing but dl. So dl gives us the change in length happening on a material. So this is how we will idealize the Hooke's law, and thereby the change in length happening on a body. So that's all for this session, and we will continue with the stress in 3 dimension and principle of superposition in the coming sessions. Thank you.